this is the last day
The MATLAB.
of the tutorial. But then after that, this was more like a regular math class. Okay, so I have a number of things to go through the tutorial. My diary here. What I'm hoping is that at the end of that, there'll be some time left so that I can take any homework questions and or something around the class for homework questions too. Whatever questions there might be. So, okay. So the first thing is one of the more fun things to deal with in MATLAB is graphics. How do we produce plots? So what I'm going to do is to demonstrate a plot. I'm going to create a vector.
You didn't create a diary.
Right. Whoops. Okay. Thank you for a reminder. Yeah, because I have my diary from 2 years ago printed out here, but it doesn't have the actual diary command in it. Because it's everything that happens after the diary command gets logged to the file. Okay, so not do that. And now I'm going to repeat those comments just so they'll show up in the diary. Okay.
So start the name of the file with .m. Would it only say? Would it save it as a .m?
Yes, it would. Yeah, well, whatever name you give it, it's going to use it.
So but whenever we're going through the command window and it will have like the output, it will show the output. But would it save the output in?
Yes. So the file name you give it does not affect the behavior of the command itself. It's going to log what it's going to log.
Okay.
So it's either going to like what you give it, or it's automatically saying that.
Yeah. Okay. So to demonstrate plotting, what we'll do is plot like a function of x. So I'm going to create a vector of equally spaced x values in the interval -1 to 1. And then notice I have square brackets, so I want to include -1 and 1. And we're going to use something that I showed you, I think it was on the first day of the tutorial, using a colon operator for like ranges of values. So I could do this. -1 is my beginning point. And then I want to have a spacing. I want to have a lot of points between -1 and 1. So I can use a spacing of 0.001, so 1/1000. So I'm going to get roughly 1,000 points, or actually 2,000 points. Okay. Now, I want to make this a column vector. I just like column vectors. It's nicer to work with in the command window. So I'm going to, so this expression right here will produce a row vector. So I will transpose it. So now I have my x values. So I'd like to plot y equals x squared. So you might think, oh, okay, I want x squared, so I can do this. And it doesn't like that. The exponentiation operator, the up arrow, can only be used on square matrices, and which include numbers, because the number is considered a 1-by-1 matrix. But what I want to do is I want to take each individual element of this vector and square it. So for that, you use the component-wise operator. So dot up arrow. That will this is component-wise exponentiation. Just like if you wanted to multiply two matrices, but not matrix multiplication, rather component-wise multiplication of entries, that would be dot star. So this will accomplish what I want. Okay, so now I'm ready to plot. So the simplest usage of a plot command, you give it your x values, and your y values. The first argument is for your horizontal axis, second argument is for your vertical axis. And now, what I've seen often when students are using the plot command, it's going to create a sub window within here, and I think that's I guess it depends on what their layout is. But what you're going to see when I do it is it creates a separate window, and if it doesn't do that for you, like if it puts it in here somewhere, you can always undock it. I just undock everything because I don't want a whole bunch of windows crammed into one thing. So here we have y equals x squared for x between -1 and 1. So this is the simplest usage of a plot command. So by default, it connects the dots, because really it's plotting this great many individual points, and it will connect them with a solid curve. But the default color is blue-ish. Okay. Any questions so far? Now, you should annotate your plots. This is something I always tell graduate students if they're doing a thesis or dissertation. Committee members will always focus on their plots. Like, what are you plotting? What does this mean? Like label your axes. And MATLAB makes it easy to do. We have a command called xlabel. And as an argument, you give a string, a text string in quotes. So in this case, I want to label the x-axis as x, and I can also label the y-axis, so I'll put y there. And I don't know if you can see this very well, but yeah, you can see x down here. And then for vertical axis label, it's going to turn it on its side. I don't think I'll have an opportunity to demonstrate this here, but when you're doing annotations like axis labels and that sort of thing, there's very limited LaTeX capability in those text strings. Like if I wanted to do, well, I'll demonstrate this using the title. For example, I want to put a Greek letter alpha in so the title is used to put a title on top of a plot. You can see that it does an alpha there. So very rudimentary LaTeX.
Can do
Yes.
a little.
Oh, LaTeX. This is how LaTeX is typically capitalized. I know it's kind of like a 7-year-old came up with it, but okay. So for instance, if you do a backslash and the name for a Greek letter spelled out, it'll produce the Greek letter for you. You can do things like subscripts, superscripts, things like that in these text parts of a plot. So both of you who are doing like an honors thesis, that sort of thing, probably won't do that. Okay. Now I want to plot something else. Like here I have y equals x squared in blue, and okay. And I'd like to plot like y equals x. Now, what this means, okay, so the y values are my x values, implying that function. But r, as the third argument, is how the curve is to be formatted. A letter can be used to indicate certain colors. So R is for red. And then the double dash here means to produce a dashed curve instead of the solid curve you see. But there's one thing, if I go ahead and do this. Okay, so we have a red dashed curve, but notice that the previous curve I have there is gone. And I didn't actually want that. Now I knew it was going to happen, but so this is, so I'll point out how you if you want to superimpose different plots, different curves on the same plot, how you do that. So use a hold command to superimpose curve on the same plot. Because by default, plot commands will wipe out whatever was already there. So what I need to do is I need to put my y equals x squared curve back. And here, this is the default behavior, but this says blue, and then the single dash is for a solid curve, as opposed to a double dash for a dash curve. So this will put the y equals x squared back. Notice my axis labels are also gone. And now, if I do hold on, so that will save whatever was already plotted there. So now I'm going to plot y equals x in red again. And now we see both. And also, it adjusted the axis limits automatically to accommodate both. Because y equals x squared only occupied this top portion here. So it'll always make sure the data fits.
If you wanted to do more than 2 variables, would it be simple enough to just have another variable?
Mean like a function of 2 variables? Or
No, like x, y, and z.
oh, okay, but are you talking about like a 3-dimensional plot? That's a separate command. So that would be plot 3. So in that case, you just specify your x, your y, and then your z. Plot and plot 3 mostly work the same way. But with plot 3, often what you're doing is, instead of plotting like y as a function of x, that's a curve, you're plotting like z equals a function of x and y, that's a surface. So there's a surf command for that. If possible, I will demonstrate that.
About the syntax.
Yeah.
So R and B stand for the colors.
Yeah.
And whatever you have in the second position is the function you have.
Okay, I'm going to pull up the help page for plot, and that shows. Okay. So there's different things. There's line style, which is what I've just been showing with the dash or double dash. There's also marker style. So here are the colors, and then here we have these are line styles over here. So you can have a few more with dotted dash dot, and then you can also do marker style, and I'm going to show that in a moment. Well, okay. Like what I've been showing is just plotting a curve, but what if you're plotting just individual data points? Then you wouldn't want them connected. But what style do you want them to be? Like suppose you're plotting several sets of individual data points, and you want that to have different marker styles to distinguish them.
Yeah.
Then you could use this.
But with whatever you showed before, like you have functions there, right? The plotting function.
In this case, yeah.
So what is in the first, like, you stick to x, the first position.
Yeah.
What is it like?
Okay. Because now you're asking about.
What does it stand for?
Oh, okay.
It's just variable.
Okay. So what it does is, these first 2 arguments to plot have to be vectors of the same dimension. So basically, if you're feeding it here are my x coordinates, here are my y coordinates.
Oh.
And these can be whatever expressions you want. And then it'll just plot them. Yeah, that's what you're saying. Okay, I want to do an example involving, I did hold on to freeze this in place, but now I want to, so one of the explorations in the first homework is plotting different powers of x on the same plot. So you would use the hold on command to do that. But if you want to stop holding these things in place, like actually do a new plot, then I could do hold off. So now the next plot command will get rid of all that stuff. So now I'm going to plot against x a function cosine x, and I'll do this. The k is for black, distinguished from blue, and then the O is to plot each individual data point as a circle. So if I go ahead and do that, the problem is I have 2,000 data points here. So really this is like 2,000 or so circles, okay, 2001, all very much mashed together. So that's not a very illuminating picture. So I'm going to make a different x vector where there's more spacing. So I'll go from -1 to 1 again, but with spacing of 0.1 instead of 0.001. And then I'll use that. Okay, here we see cosine x from -1 to 1, individual black circles. Now, if I wanted circles and connected, I could do like k-o, and that would do both. So you can specify a color, a marker style, and a line style. And if you leave out any of those, it'll just use the default. Okay. Now, it gives a title. Goes up top. And then I'm going to add another curve to show you another feature. I'll plot y equals x again, but using this x. Red. Okay. Oh, dang it. Got the whole on. Right here. Okay, let's try it again. Okay, once.
Oh, what?
I forgot to do something. Okay, I need to do a hold on.
I don't play with the font. Yeah, wait, what?
Oh, I just made up a title to put there.
But my stopper part is title playing with fonts, the first one.
Yeah, I'm just recreating the plot that I had a second ago. Okay, so then what I forgot to do last time, I have to do hold on before I plot my second, or just plotting y equals x again, but using x2, using a red dashed line. Okay, so now we see both. So here's y equals x, red dash curve, and we have y equals cosine x, the black circles. Okay. Now, what you can do, there's a command called legend to have like if you have multiple curves and you want to indicate what they are, you can like you want to have a little legend in your plot that describes each of these curves. The legend command will do that. So what I will do right now is legend. Now the first curve I plotted was cosine, so I'll make that the label for the first curve. And then the second curve I plotted was just y equals x, so I'll use x as the second label. Okay. And then don't know how I can see it. It's way up here in the upper right corner. So we have, so what it did is it matches the label cosine with the line or marker style of the curve. So black circle for cosine and then red dash for x. There are additional options for legend that I won't get into now to affect how this is placed. Here, the upper right corner might not be the best placement because it's overlapping the data. Like I might prefer that it's down here. But again, so if you look at the help page for legend, you can see how to control the placement of that legend box. Okay. Another command for if you just want to place text anywhere within a plot, but this is only for two-dimensional plots, called gtext. So I'll just give it a text string. So what will happen is once I hit enter, it's going to allow me to pinpoint exactly on the plot where I want this text to go. This is good for labeling certain features of a plot. So now I'm moving my cursor around and I'm just moving it around my mouse until I figure out where I want to put the text, and then I'll click, like I want to put it right here, and that's where the text appears. But I found this useful for, like, if there's certain features on the graph I want to
Wait,
put labels at.
where do I put it?
Okay. Oh yeah, so pick wherever you want. So as soon as you tap, that's where it puts it. Now let's suppose I messed up and it put it places a text and maybe I don't really want it there. Notice the arrow right here at the top of your figure window. If you select that, it gives you a way to edit various features of your plot. Notice it's sort of selected the whole plot. So what I can do is once I've clicked on this arrow, I can click on the text, and now notice I've selected the text box. So now I can move this around. So I can put it wherever I want. I can put it over here. I can also use this to delete features of a plot. For example, suppose I don't want this red dashed line anymore. I can click on it. Notice it's selected now.
Wait, what? When you say select,
Yeah, click on the line. Okay, so notice the circles there, the blue circles that pop up. That tells you that it's selected. So now, if I were to hit the delete key,
delete key,
yeah, now that red dashed line is gone. Also notice it adjusted the axis limits.
but do we want it gone?
Well, in this case I did. Because I wanted to show you that you can delete something. And so, yeah, it's gone. Now, if you didn't really want to do that, I think you can undo. I'm going to try undoing. So for Mac, it's Command Z. Yeah, undo.
Command Z,
Or your Windows, do Control Z. Did it put it back?
yes.
Okay. So, yeah. So these are those things you can undo. Okay. All right. Okay. Any questions about any graphics things that I've done so far? Okay. Now, the figure command by itself creates a new figure window, a blank one. Okay, so there it is. But you can also use figure with a numeric argument. Like here, I already had figure 1, so when I said figure, it just uses the next number. So in this case, figure 2. I could also do, for instance, figure 10. And that will also create a new figure window and assign it to the number I gave it, 10. Now, another thing you can do, you can have multiple plots within the same figure window, like multiple sets of axes, using the subplot command.
What do we do as figure 2?
Oh, I didn't do anything with it. Actually, I'm just gonna close it. But I still have figure 10. Okay. So, okay, actually, what I would suggest, okay, I'm not gonna do anything more with figure 1. Go ahead and close that one too, if you're following along. I just wanna have one figure window open at a time. Okay, let's not have just this one figure 10. So the subplot command is used to create a matrix of axes on a single figure window. So for instance, what this does, subplot 231 creates a 2x3 matrix of axes. So 2 rows, 3 columns. And then the third argument, the 1, that tells you which one is active, meaning that any plot statements will work on that set of axes. I'll show you what I mean. Okay, so this is what it does. So it creates this one set of axes, but notice it's very small because it's making space for 2 rows of 3 sets of axes. So 6 sets of axes in total. So now, if I go ahead and use a plot statement, I'll do plot x and then expx, the exponential function. Then it's going to go to this set of axes. So then any other graphics operations will work with this set of axes until I tell it to change. So for example, if I do subplot 232, now it's gone to another set of axes. Still the same 2x3 matrix, but now I've told it that plot number 2 is active. The way they're numbered is 1, 2, 3, 4, 5, 6. So it's numbered in like what's called row major order, first row, second row, and so on, to indicate which set of axes you're actually working with. So for example, if I want to plot x cubed, then it goes to second set of axes, and I can keep going. So, I mean, if you're doing a document like a LaTeX document, and you want to have an arrangement of plots, you could do that with individual image files if you want it, but you can also do it this way by having all of your figures in one MATLAB figure window, and then you save that as just one image. So that can be good for your presentations and such. Speaking of which, suppose I did want to save this as an image file. Okay, so if you go to the File menu and do Save As, so I can save an image here, and notice the format, MATLAB figure.fig. That is not an image format, but it's probably the most important format you can use. Okay, so I'm going to give it a name. It filled in untitled, I just changed it to subplot. That's the .fig. Okay, now, when you create a plot in MATLAB and you want to save it, like to include it in a homework assignment or a presentation or document, always save the .fig file first. Okay, so now I have that .fig file. And you can then save it again using some image format. Here's several standard image formats down here. Like I like to use the .png for quality graphics.
You wanna save it again?
Yes, I'll
Wanna save
explain,
that again?
but in a different format.
What format?
.png,
Portable what?
portable network graphics.
Subplots.
When you save it as an image format, depending on, I don't know if it works the same on Windows versus Mac, but
Subplot.
right when I hit save, watch the figure window. It's gonna flash for a bit. Yeah, there, when it's actually saving. Now, the .png, the image file, like a .png or .jpeg or whatever you have, that's what you actually include in your document. But the .fig is helpful because suppose you want to go back to, like, let's suppose you include this image in your document, and then you send it to your professor, your advisor, and they say, oh, this is a great plot, but I want you to change this one little thing. And if all you have is the image file, you have to repeat all your MATLAB statements and recreate that again. And I don't like to torture my students that much. So, but if you have a .fig file, what I'm going to do is I'm going to close this right now, and then I'm going to open the .fig file.
You're closing it?
Yeah. So I open the .fig file, and there it is again. So now you don't have to perform the computations all over again that led to the figure file. You just pick up where you left off, and I can go ahead and annotate this. So if you save the .fig file, it makes your life a whole lot easier when you have to make changes. Okay. All right, any questions about graphics? Okay. Close this window.
Wait, I do.
Yes.
So when you save the fig file, if you are making changes to it after, does it autosave or do you have to do something to like resave it?
You should resave it.
Okay.
Yeah. I'm going to create random vectors here. X, an X, a Y, and a Z. So here's the X. Do the same for Y. Then Z.
Brand. That
So then what I can do is, if I do plot 3, this is a 3D plot, X, Y, Z, and I'll use red circles, so same kind of specification as for a 2-dimensional plot.
Plot 3.
Yeah, so plot 3 instead of plot. So now this is a 3-dimensional plot, so you can see we have a X, Y, and Z set of axes. And I can click on this button here I can rotate in 3 dimensions. Also, having this space is kind of hard to get a good perspective on. I can do grid, and that puts some grid lines in, so I can better understand what I'm looking at. Unfortunately, I don't have time to show more about the 3D case, but just as plot is perfectly good for plotting y as a function of x, the surf command is good for plotting z as a function of x and y. Next, polynomials. when we work with polynomials in MATLAB. So MATLAB is a standard format for representing polynomials. Represents polynomials using a row vector, I emphasize row vector, of coefficients. And they're ordered from, it's very important, highest degree, lowest. So, for example, suppose I wanted to represent this polynomial, x squared minus 5x plus 6. So I'm going to make a row vector. First is the coefficient of x squared, highest degree and lowest, that would be 1. And then the coefficient of x, which is minus 5. And then the constant term, 6. And so I'm going to make this row vector p. So p represents this polynomial. Now, first, there are several polynomials. Let's see if it gives you the list. If I do help polyfun, okay, there's a lot here, not all of which is useful to us, but there's a whole list of functions that are useful for polynomials and also doing interpolation. But polynomial functions are listed, where are they? Oh, these at the bottom. Okay. Figured. I want to show you this one, roots. So roots finds the roots of a given polynomial. So if we have a polynomial that I'll refresh your memory, x squared minus 5x plus 6. Now that's something that you can go all college algebra and figure out the roots. So you know what they should be. So this is the syntax. P. Yeah, I created P earlier. Do you have?
No, I'm trying to catch up. You're too fast.
I have a lot to cover. But you can always ask me to stop.
Okay.
So roots with the given polynomial vector as an argument will compute the roots of this polynomial and return them in a column vector R. So if I do that right here, so the roots, because this polynomial factors into x minus 3 and x minus 2, so the roots are 2 and 3. So the roots will compute polynomial roots for you. And that's true even if the polynomial has complex roots. So if I do another example, b equals 1, 0, 4, and that's for a polynomial x squared plus 4. So we have, now that polynomial has complex roots. Because you end up with x, trying to solve x squared plus 4 equals 0, you have x squared equals minus 4. So if I do roots p on this one, I get plus or minus 2i. So far about roots for polynomial. Now, roots takes as input the coefficients, and the output is the roots. Now, there's an inverse to that in a way. If I do poly takes as input for roots and gives you the coefficients. So So this computes coefficients of a monic polynomial with these given roots. Anyone remember, like, from another class, what is a monic polynomial? I don't know if that's mentioned in the class like one or something like that.
Like in Cal 3.
I don't know if I brought it up in that class. A monic polynomial is one whose leading coefficient or highest degree coefficient is equal to
Wait.
1.
Wait, you didn't type one.
So, well, I don't have to. Because, okay, the input to poly are not coefficients, they're roots. I want the coefficients of a polynomial that has roots 3 and 2. So if I do that, it gives me x squared minus 5x plus 6, or those coefficients. So in other words, so what that means is, roots and poly, they're somewhat inverses of each other. So if I do this, poly of 2 and 3, that gives me the coefficient of a polynomial, and then I feed that as an input to roots. It should basically cancel each other out. Because I have roots, I get the coefficients of a polynomial with those roots, if I compute the roots of a polynomial.
Roots, poly?
Yeah, roots of poly of a vector should give you the same vector back, although the order is not necessarily the same. So, in other words, poly goes from roots to coefficients, whereas roots goes from coefficients to roots. So they're the same process in opposite order. Now, that should work with whatever vector I give it, we think. Let's find out. If I do roots of poly, let's say 1:5, so that's those numbers 1, 2, 3, 4, 5. I should get the numbers back 1, 2, 3, 4, 5, just in a different order maybe. Let's see what happens. Well, okay, that looks pretty good, but I'm going to do format long. I want to see 15 decimal places. So if I do that again, okay, well, there's some rounding error here. So this number is approximately 5. The next number is slightly less than 4. So there's some error introduced, and we're going to learn more about rounding error in the next chapter, but I want to demonstrate that. So, so roots of poly of x is approximately x with rounding error. But rounding error, how big can that rounding error be? Let's look at another. If I do, instead of 1 to 5, if I do 1 to 20, you think I get 1 to 20 back? Well, not really. It's
Roots what? Roots poly what?
1:20. Sorry.
Roots poly what?
So that gives you numbers 1 to 20, except there's more round off error. It's not so good now. Here 20 is only 2 decimal places correct. Here it's really only 1 decimal place correct. We're 14.95. It should be 15. So what we see is the higher degree polynomial I'm dealing with, the greater the round off error. And if I do this one more time, roots poly of 1 to 50.
Who's calling?
And don't forget, you can use the up arrow to bring back your previous command so you can edit it. It saves you some typing time. So I'm supposed to get the vector 1 to 50 back, but when I do, the round up there is so bad that the numbers I'm getting are complex. So polynomial root finding, you think we have that problem down, but we really don't, and only for certain nice cases. Yeah, because I mean, yeah, this is not even close. So, whoops. Okay, so wire to where? So that's going to be back between roots and coefficients. But there are other polynomial functions that are also of interest. Want to evaluate a polynomial? That's polyval. Okay, so to show you that, I'm going to make up a polynomial. 1, 0, 0. So this is a polynomial x squared. So what I can do is polyval takes in this first argument the polynomial you want to evaluate. And then the second argument, the x values that you want to plug into it. It could be a single number, it could be a vector, it could be a matrix, whatever it is. So in this case, I'm going to evaluate this polynomial as numbers 1 to 4, 1, 2, 3, 4. So this is a column vector consisting of 1, 2, 3, 4. So it's just going to square these, so it should give me 1, 2, 3, 4 all squared, and sure enough, it does. At least it did that right. Well, I'm trouble keeping track of my pages here. Okay. All right, so that's polynomial evaluation. Here's some other ones. The basic calculus operation of polynomials. So I'll go ahead and bring this polynomial back. 1 minus 5 and 6. That's x squared minus 5x plus 6. Okay. If I want a derivative, I can do polyder, for derivative. So what should the derivative of this be? Any one.
X minus 5.
Yes, and sure enough, 2x minus 5, so it gives you the vector coefficients. We can also do antiderivative. And that function is polyint. Now, if I take what I just got, the answer of 2x minus 5, it'll compute the antiderivative of that. But it gives me x squared minus 5x plus 0. Because, of course, the antiderivative is not unique. So polyint assumes a constant of integration. In other words, the plus c of 0. So any output of polyint will always have a 0 for the constant term. The question of the polynomial functions so far. also a function for multiplying polynomials called conv. That seems like a strange name, but conv is for convolution. So it's useful for a variety of things, because it happens to be useful for polynomial multiplication. So I'm going to make up two polynomials. So 1 minus 5, so this is x minus 5, and then q would be 1 plus 5, but x plus 5. So if I multiply these together, what should I get?
X squared minus 25.
Yeah, so x squared minus 5 squared. So if I do that, so I'll do conv p and q, and sure enough, x squared plus 0x minus 25.
Wait. Ah, man, it got the wrong thing. Tried to comma and then
Oh,
I can't go.
like I said earlier, stop that. Don't do that. Use the up arrow to bring your command back. Keep going. Yeah. Now you can fix it. Yeah. Okay. Now hit enter. Okay. Now do the conv again. Okay. Now, conv. Okay, so you have a function you can use for multiplying polynomials. There isn't a function specifically for adding or subtracting polynomials, because polynomials are row vectors. So the idea is that you would add the vectors. So the trouble is, if polynomials of different degrees, the vectors have different lengths. So it's something that you have to be careful about. So if I do an example of lost my place again. Fortunately, pages are not numbered. Okay. Here we go. So for example, these polynomials right here, x plus 5, x minus 5, if I were to add them, they have the same degree. So definitely don't need pages anymore. Sorry. So if I were to add these, p plus q, and x minus 5 and x plus 5, if I add them, I should get just 2x minus 5 and a 5 will cancel. And sure enough, that's what I get. This is a polynomial. This is x plus 5 plus x minus 5 is equal to just 2x. And this is these are coefficients of 2x. But now, if I were to change p to something else, by default, my go-to polynomial here, x squared minus 5x plus 6. So p is of degree 2, and q is of degree 1. So if I do p plus q, that's narrow. So that's unfortunate. How to get around that is if so you pass lower degree polynomial, with zeros as needed. So I can do something like this. P plus, and I have 0 and then Q. Because P is of a degree 1 higher than that of Q, I need to add 1 0 in here. And that'll do it, because I have x squared minus 5x equals 6, plus x plus 5 is equal to x squared minus 4x plus 11. That's sure enough what we got. So I need to be careful about the polynomial addition and subtraction. The vectors have to have the same length. Okay. So I have a polynomials formatting. We've seen some things about formatting before, like format long, format short, to use like a certain number of decimal places, but there are other formats too. If I set x equal to pi, so that's a special variable that gives me value of pi. What you see here is format long, and you see what format short. If I display x again, okay, that's just 4 decimal places. That we've seen. Now, another format is format rat. Rat is short for rational in this case. Suppose you have a number that you expect to be a fraction, like it should be like exactly equal or very much almost equal to a rational number. You can do format rat, and it'll display it as a fraction. So if I do like 0.25, it displays it as 1/4. Now, I could try displaying pi as a rational number. Of course, we know that pi is not rational. But it's going to give me an approximate fraction. So this is an approximation to pi. Let's see how accurate it is. But for that, I have to go back to an ordinary numeric format. And if I do 355 over 113 minus pi, well, that's the error. This is pretty accurate. It does what it can.
Minus pi.
Yes. Yeah. So 355 over 113 is the difference from pi by this small number here. Is a pretty good approximation of pi. Right. I'll set x equals some random number, 6.476. That's the default display, scientific notation. Another format is format bang for dollars and cents. So that's just going to use 2 decimal places. And then my favorite format hex, which gives what appears to be complete garbage. Hex is short for hexadecimal, base 16. It uses digits 0 through 9, and then the letters A through F for the hexadecimal digits 10 through 15. This is useful for understanding how floating point numbers are represented internally. When we get to computer arithmetic, I'll talk more about that and how I'll tell you how to actually decipher this. And it can be quite illuminating about how floating point numbers work. Oh. Yeah. Not supposed to apply. Okay. Any questions about formatting? Okay. Another important concept is called anonymous functions. Because when you're working a problem on paper, like dealing with y equals f of x, expressions like that, and it'd be nice to I've also used those kind of expressions within MATLAB too. Like you can always define a function using an M file, and we've seen that last time. But if your function is particularly simple, you don't have to go to trouble creating an M file for every little thing. So as an example, I'm going to create an anonymous function for this function here. F of x is exponential of sine 2x. So how I would do that, I create a variable f that's called a function handle. So I say f equals, and the at sign tells MATLAB that this is meant to be a function. And then after the at sign, you indicate what are its inputs. In this case, I'm just creating a function of x. After the at sign and the parentheses x, I give the actual expression for a function. Exponential of sine of 2 times x. I need to change back to the format. So now I can plug x values into this function. I could do, for instance, f of 0. So sine 0 is 0, e to the 0 is 1, so sure enough I get 1. I can, in this case, I can pass random values. Here I create a random vector. I pass that into f. So it's going to evaluate this function at all of these values. So this is how you can define functions, especially ones of relatively simple expressions, without you can do this like on the fly without creating a whole new M file. You can make functions with more than one variable. Like if I do f at sign, if I have x, y, and I'll use x squared plus y squared. So now I can do f2, 1. So it assumes that x is 2 and y is 1, just by the ordering. So that will give me 5. What if I wanted to do this? What if I wanted to pass vectors? So x is vector 2 and 3, y is vector 4 and 5. So I wanted to do, for the first element, 2 squared plus 4 squared. And then for the second element, 3 squared plus 5 squared. But if I do this, that's an error. Anyone tell me, given the way I defined this function here, why doing this was fine, but doing this is
not.
Yeah, what did I do wrong? How should I define this function differently? So it still does x squared plus y squared, but it works just as well for vectors as it does for numbers.
Would you have to have that dot?
The dot. Yeah, so if I redefine the function, do x dot squared and y dot squared, then it will do it.
Will it have an error if you do dot squared without meeting
Dot squared what without?
without meeting it?
Oh, no. Yeah, so it doesn't hurt to have it. Well, okay, here's something to keep in mind. Well, okay. And as long as you make sure that's doing what you really want. But yeah, if you use it when a scalar was not necessary, as I found my students do all the time, it knows.
If you're dealing with, sometimes you're dealing with vectors with plugging in
Yeah.
scalars in.
Yeah.
Different type each time.
Yeah, because it thinks of the numbers of 1 by 1 matrix.
Yeah.
Yeah, so first here we have 2 squared plus 4 squared, so that'd be 20. And then 3 squared plus 5 squared, so 9 plus 25, 34. All right. Here's some other functions that are often useful. I'm gonna create a random matrix here, 3 rows, 2 columns, to demonstrate them. The size function gives you the dimensions of a matrix. So I do size of A, that will give me a row vector indicating all the dimensions, 3 rows, 2 columns. Another thing you can do is, or I can call it this way, m comma n equals size of A. So that way it'll assign the rows to m and the columns to n. Let's see, m equals 3, n equals 2. You might find that form more convenient. If I have a vector, 1, 2, 3, I can do length. That gives you the length of a vector. But it doesn't matter whether it's a row vector or a column vector, it will give you the number of elements. Both functions I find myself using all the time. There's also, I have a matrix here, A. You can, well, if I want to reshape the matrix, I reshape A into, let's say I want to reshape it into a row vector. So I tell reshape what I want to reshape, and how many rows in the result, and how many columns in the result. This will give you a row vector. But how will it fill in the row vector? Notice what it does. It takes this number first, then this one, then this one. In other words, it goes through the first column to fill in my row vector, and then it goes to the second column. So reshape works in what is called column major order. So it is anytime you're traversing all the elements of a matrix, iterating through all of them, it's going to go column by column. Whereas row major order is row by row. Different programming languages use different ordering conventions for how they store matrices in memory. Fortran is column major, so that's why MATLAB is too. C and C++ are row major. Just to make things more complicated. Our convenience functions, sum. Okay. In my vector x I had before, 1, 2, 3. Sum of x, that just adds all the elements of a vector. So in this case, it's going to add them all up and give me 6. Similarly, prod multiplies all the elements. So it should multiply, oh, well, in case it can multiply these and also give me 6. So maybe it wasn't the best example. Here's the functions that will just give you 6. Now, there's actually an exploration, one of the last ones in the assignment that discusses usage of sum on matrices. So applying sum to a matrix is not just going to add up all the elements of a matrix, but in that problem you'll see what it does. Okay. That is the end of the tutorial part. So I'm going to do a diary off, but for just to save that part of it. During any remaining time, we have a few minutes left, but also immediately after class. Any problems with the first homework?
Yes,
Okay,
so many. Yes, so many too.
okay, what do you got?
Yeah, just about just about everything.
Okay.
Like the latter parts of exploration 1 and so forth.
Okay. Oh, what specifically?
Part 2 and 3 of exploration.
Oh, hold on, I'm gonna put this up on the screen. Okay. The idea behind this, like in the first part, you assigned A equal 1, B equal -5, C equal 6. Now, quadratic formula, okay, so you know the quadratic formula in terms of A, B, and C. The idea is that you would actually type at the prompt using MATLAB syntax the quadratic formula, like so minus b plus square root of b squared minus 4ac over 2a, and you do it twice, once for a plus sign and once for a minus. So the idea is just typing out the quadratic formula in MATLAB syntax. And since you know what the roots of the polynomial of these coefficients should be, ax squared plus bx plus c, that's the polynomial we've been seeing today, you should get the values 2 and 3 when you use a quadratic formula. So that's all I'm asking for in the second part. That you use MATLAB syntax to type the quadratic formula at the prompt. Using the variables a, b, and c that were defined in the first part.
But homework check. Homework text.
Sorry, what? I don't understand.
How do I make changes in the homework 1 text?
Wait. Okay.
How do I get rid of the undesirable?
Well, yes. So you
What
can
do I do
edit.
about getting rid of the undesirable ones?
Oh, yeah. You can just edit it. You could just go ahead and delete anything you want to in this file. Yeah, because you're editing it just like any other file. Yeah, you can delete all that, for instance.
All of this.
Yep. For the third part of this problem,
Sure. Explode.
what? But again, using MATLAB syntax to type out this expression. But to represent pi, I said to solve this equation, tangent of pi over 4 equals 1, because, well, what expression for pi does this give you? If you solve this equation for pi, anyone?
Okay, square 2 over 2, that's 16?
No. This equation, if I rearrange this equation to isolate pi,
Oh, that's R2.
So-
yeah, arctangent.
Yes.
Yeah, 4 times arctangent of 1.
So for exploration. I'm trying to. That would be. So diary homework documents. Reopen. So diary homework 1 dot reopen the whole.
Yeah, that's if you keep adding to that file. Okay, we've appreciate the class time, so anyone wants to leave, go ahead and leave. But anyone who wants to have questions answered, stick around. Oh, I'm gonna stop the recording though.